Good morning and welcome to 2330, Introduction to Organic Chemistry. We're going to continue with Chapter 5, which is Reactions of Alkenes and Alkynes. And we might even get into Chapter 6 today, but we'll start getting that first. Is our exam on the 18th of the 25th, the syllabus and lecture schedule saying different dates. Definitely go with the lecture schedule on that one. Let me double check that on Canvas real quick. I thought they were the same, but the lecture schedule is the most accurate. I'm pulling up the lecture schedule now. Yeah, because it has the lecture schedule for the chapters 4 and 5 are going to be this week, and we're already on chapter 5, so we're actually going to be a little ahead. And then, no, we're on chapters 5 and 7. So we're going to finish chapter 5, start chapter 7 today. And then all of next week is going to be chirality, which is a little bit of a challenge. So I wanted to spend the whole week on it. And then we'll have our review and our exam on the 25th of February. Okay. So thank you for finding that out. I will have to look in the syllabus and see why it's a different date, but it is the 25th of February is our next exam, our first exam actually. Okay, so let me double check something real quick. Yes, I do. There we go. Okay, so where we left off last time, we were talking about regioselectivity and stereoselectivity. So regioselectivity is putting groups exactly where you want, and stereoselectivity is showing you that they add in different ways. And so let's share my screen and continue on with that, looking at the hydrogenation of alkenes and alkynes. Okay, I'm going to put the gallery view up here. There you go. And I'm going to move this and hopefully it stays there. Can everybody see that screen about regioselectivity and Syn stereoselectivity? All right, great, thank you. So as we learned, we had that about these things that were very different materials like water and HBr and this borohydride. They added across the double bond in a specific way. The borohydride here is the first one to add where both atoms were on the same side of the molecule. The other ones added either anti or it didn't matter because they made a carbocation. Now, when we go to the hydrogenation of this, we actually get to, we'll see the regioselectivity that the stereoselectivity of that, because we're going to add hydrogen in a specific way. Okay, so hydrogen itself is not reactive enough to just go ahead and add across there. So we typically use some kind of catalyst to activate the hydrogen to get it to add across that double bond. Okay, let me see, nobody in the way here. All right, so we call that a catalytic reaction or a catalytic hydrogenation. Without that noble metal like a platinum, palladium, or nickel, they would not go. Also look that it needs a little bit of pressure. Hydrogen's a gas at room temperature, so you need a little bit of pressure to try to drive it into the solution to help the reaction go. Now, it's hard to tell exactly the syn and anti of these things because when we add that hydrogen across that double bond, one hydrogen goes one way and one goes on the other side, and we really can't see what's happening. But there is a certain stepwise method that happens when we do this reduction of alkenes. So reduction means the addition of hydrogens. Oxidation is going to mean the removal of hydrogens. So keep that in your list of words to remember. Okay, so the most common pattern we have is the Syn addition of hydrogen. It means both hydrogens add across the same side of the double bond. And most of these catalytic hydrogenations undergo that Syn addition because you're interacting at the surface of the molecule. Okay, so if we look at that, how do we know? How do we know that it's adding on there? Well, that's why, again, we're going back to the cyclohexane. The cyclohexane means it can't rotate around, so we actually can tell where the hydrogens are adding. So in the case of this alkene, we have our alkene here, and what's going to happen is the hydrogen is going to add to the bottom on this side and the bottom on this side, kicking both of our methyl groups up and out of the plane. Remember, the solid wedge is up and out of the plane. We get 70 to 85% of the product is that way. okay? And then there's a little bit less of the trans, where one of the hydrogens hit from the bottom, but the other hydrogen actually came on the top, pushing that methyl group down, okay? So it tends to be mostly Syn addition, where the two hydrogens are adding across the same side of the double bond. Okay, so why is it mostly Syn addition? Well, it has to do with the fact that we are on the surface of that metal. And the first thing that happens is that hydrogen comes down and reacts with the surface of the metal such that the hydrogen molecules are actually all chemically bound to the surface of that molecule. Okay, so the next thing that has to happen is that the alkene has to come down, and that pi bond has to interact with that surface as well. Once that alkene interacts with that pi bond, we have an adjacent hydrogen able to come over, have these electrons move over to grab that hydrogen to create our new sigma bond, and then we have it happen on the other side. And if there's enough hydrogen here so that there's really close proximity, it doesn't have time to rotate or move. And so we can have the other electrons reach out and grab the other hydrogen to give us our addition where both hydrogens are on the same side of the molecule. Okay. So that gives us an idea of why it has to be on the same side, because we've actually laid it down on the surface and are reacting it right at the surface as well. Okay, so now when we talk about this, we're going to see about the idea of the heat of hydrogenation gives us an idea of the stability or the instability of an alkene. So what we're going to do is we're going to say the amount of heat given off, so you notice it's a negative number in kilojoules, is the amount of energy that was stored in that double bond. Okay, so that means as we get to as we change that amount of energy given off, we have a different amount of energy that was stored. In this case here, we have ethylene, which is going to do just those two carbons. We're going to add two hydrogens across this double bond. And when we do that right here, we give off 137 kcals per mole of heat. Okay. Just by adding this right here, we actually give off less heat. So wait a minute, it's giving off less heat. So it might have been more stable, okay, because less heat was given off during the hydrogenation to go back to the alkane. And when we have this, we just add another carbon here, it's about the same. But now we have this cis butene, it gives off less energy, okay? So between the internal alkene and the terminal alkene, it actually is more stable, okay? Now, when we go to the trans alkene, it gives off even less energy, which means the trans alkene is more stable than the cis alkene, okay? So we see how that correlation of heat given off correlates to stability of the compound as a whole. And then by a third substitution, it drops again. And the fourth substitution, it drops even more to our lowest level here. So what this means is our tetra-substituted alkenes are our most stable alkenes. And so when we're looking for products that are more stable, we're going to look for that more substituted alkene. Okay. So do we understand that, what this means? The heat given off correlates to the stability of the alkene we reacted with. Okay, I felt a cough coming on, but I think I averted. Okay, so in the case of our hydrogenation, the reduction involves a net conversion of the weaker pi bond to a stronger sigma bond, okay? The greater degree of substitution on that bond, the lower of heat of hydration. The greater degree of hydration, the more stable the double bond, okay? So if you have 4 carbons bonded to your alkene, it is more stable than something with just 1 or no carbons bonded on it. We also saw that the trans alkene was more stable than the cis alkene because of the amount of heat given off. Okay. So And the whole point on the transalkene versus cisalkene is those two groups on the same side can kind of push against each other, giving a little bit of strain, which is why it's just a little less stable than the trans configuration of the system. Okay, so, and here's an example of that. So in the case of the transbutene, those methyl groups don't see each other, and they only have interactions with the hydrogens nearby. So it's only the hydrogens here that are interacting here. And so that's, hydrogens are very small. Methyl groups are much larger than the hydrogen. So that when they're on the same side, the electrons from this methyl group are butting up against the electrons on that methyl group. And that's giving that difference of about 4 kcals per mole in our energy stability. And if these groups get bigger and they're still cis, it'll be a more pronounced interaction because that strain will be higher and higher. And we can measure that by the heat of hydration. So this is a really cool experimental way of determining yes or no about your theoretical supposition that this molecule is more stable than that molecule. Well, let's hydrogenate it and find out if we're right or not. So this is a nice, tangible experiment. We can prove our theoretical observation. Okay, so that's what we do for alkenes. And as we saw in alkynes, there's a major difference in their chemistries, including acidity and basicity of the alkyne. We saw that alkynyl hydrogen was very acidic. However, when we do that reduction, we're just going to talk about the reactions of alkynes now. All right, so this is the hydrogenation of alkenes. Is there any questions on the hydrogenation of alkenes? We're going to hydrogenate alkynes too, but I want to go through a couple other reactions they do first.
So the general rule of thumb is that the larger the molecule, the more stable it is.
The more substitutions, the more carbon substitutions on the alkene. So notice that in the table, there was not much difference just by the molecule getting larger right here between the propyl and the butene right here. The fact is there's still one carbon attached to the alkene, and they're about the same. So this is also a butene, but it's much more stable because there's a carbon on each side of the alkene. So it's the number of carbons attached to your alkene increases the stability. So by the time we get to 4, it's the most stable. Okay?
And those carbons that are attached and are substituted, they're sigma bonds, so they're stronger?
Yes. Well, yes, these sigma bonds are definitely stronger than the pi bond here. But that pi bond itself is weaker than the 2 new sigma bonds we get when we add hydrogen across it. Because that carbon-hydrogen bond is a sigma bond. So we actually gain that stronger bond by removing the pi bond and adding the hydrogens.
Okay, thank you.
So, but yeah, all of the other ones are just sigma bonds, and they are stronger bonds than the pi bond. However, I wanted the description of a weak pi bond going to 2 strong sigma bonds has everything about the hydrogens that are being added. Okay. So now let's talk about the reactions we have of alkynes. So alkynes are just 2 double bonds orthogonal to each other. One's in the X plane, one's in the Y plane, and they're above and below the sigma bond, okay? And they have a different hybridization than the alkenes. And that gives rise to a very interesting thing, is that the acidity of the alkynyl hydrogen is much, much higher than that of the alkene or the alkane. And it's not as acidic as the proton on water. Okay, so what we're going to be able to do here is that with a decent strong base, we should be able to pull that proton off and then use that alkyne anion as some kind of reactant. Okay, so when we do that, we typically look at the acid and base strength. Remember we were talking about that? And if we look at the pKa of our alkyne, and we try to use water or hydroxide as the base, what happens is when it pulls this proton off, it becomes water, okay? This hydroxide pulls the proton off and becomes water. And our water has a pKa of 15.7, but our alkyne only had a pKa of 25. What this means is hydroxide is not a strong enough base to remove, I'm trying to admit somebody here, okay, to remove that proton. So that means we have to go to a stronger base to do that. And when we have a carbon anion, we saw that the nitrogen anions are actually stronger bases. And so we need to go to that sodium amide or that NaNH2 to remove that proton. Okay, so if we look at that reaction, we can do that with that sodium amide. And instead of this right here, we're going to use sodium here with a negative charge on it to deprotonate that to give us our strong base. Okay, so what can we do with that strong base? Well, the cool thing is we can use it to make new sigma bonds. It has electrons. It's a Lewis base. And so we call that the nucleophile, looking for positive charge, right? So those electrons of that negative charge can reach out and create a new sigma bond with something else. And in this case, it's going to attack the carbon of this polar bond between carbon and chlorine and create a new carbon-carbon bond, first time we've done that, and kick out the chlorine to give us our final product. So what did we do? We took sodium amide, pulled that proton off, and then that formed ammonia, and that went away. We've got our anion here now that can act as a nucleophile, okay? So that means by contrast, the other side had to be the electrophile or the Lewis acid, okay? So the cool thing here is that it only works with the hydrogen at the end of the alkyne. Once you substitute one side and you now have only one hydrogen, but you can now deprotonate the other side and do that. But once you have carbon-carbon bonds there, you no longer have that acid proton on that alkyne, and you actually can grow these chains really big. You can put the alkyne right in the middle of the chain. Okay, so let's do that. Let's start with acetylene, and you can't do it all at once because you can't pull both of those hydrogens off at the same time. It's very hard. So what we're going to do is we're going to add sodium amide right here. And then we're going to add something that it's going to react with. And in this case, we're going to do this alkyl, this ethyl with a bromine on it. So what's going to happen is that acetylide ion is going to displace that bromine, creating a new carbon-carbon bond, which gives us our first compound here, which is butyne. So we went from acetylene or ethyne to 1-butyne. But we still have an acidic hydrogen. So with that acidic hydrogen, we take it off with sodium amide, and now we can react it with a different reagent. Notice this is propyl bromide, okay? So we're actually putting 3 carbons on the other side of the chain. So what we can end up with is an unsymmetrical alkyne. We have 2 carbons on this side, we have our alkyne, we have 3 carbons on that side. So we can do this for a number of different ways. And in chapter 7, we're going to discuss a lot about the types of substrates. For example, this bromide here, these halogenated materials that will work very well in this reaction. Some of them do, some of them don't. And so we're going to talk about that, but we're going to talk about that in chapter 7. All right, questions about forming an anion out of acetylene and using it as a nucleophile to attack other species.
Just a minor one. So
Okay.
why is it called acetylene and not acetyline? Because there's a triple bond there.
Yeah. Oh, yeah. It's acetylene is how you pronounce it because that's the common name. The IUPAC name would be ethyne.
Okay, thank you.
So this is the engineering name, but yeah, it's acetylene. Acetylene is how it's pronounced, but it would be ethyne in IUPAC names. And notice we did use the IUPAC name here and here. Okay, good call. Thank you. All right. So I said like alkenes, we can reduce that double bond by adding hydrogen across there. We have 2 double bonds in alkynes, so we can actually do the same thing. Using the same catalyst and about the same reaction conditions, It just takes a little more hydrogen. You have to have two equivalents, one for the first double bond, one for the second double bond. And it'll convert it all the way down to the alkane. And so once the alkane's done, it's, you know, as reduced as we can go. However, what if you wanted to stop it at an alkene? Okay, that condition where you had that platinum, palladium, or nickel catalyst with hydrogen will reduce the first double bond down to an alkene, and we already know those reaction conditions reduce the alkenes down to alkanes. So what if we wanted to stop there? Well, if we wanted to stop there, we have to do what we call poison the catalyst. And so that is what we call the Lindlier Catalyst, where we take our palladium and then we reduce its activity by adding calcium carbonate and lead salts. This is called poisoning the catalyst with lead. Okay. Once we do that, we actually end up getting a very Syn stereoselective reaction. So again, it's going to come down on the surface, but the surface is less reactive. So it's going to add two hydrogens across one of the double bonds. And then when it drifts away and comes back, it's not reactive enough to react with just the alkene. It only reacts with the alkyne. So that gives us selectivity in reactions. And we're going to see this again and again and again. Selectivity of the reagents gives us the exact material we want. And so you're going to start to see this in oxidations and reductions and other things that we do. And this is the first time we get to see it here. So that's something to pay attention to as you're making notes. Ooh, this, I have to use a specific catalyst to get a specific product. Okay, so starting with acetylene and any other necessary reagents, propose a synthesis for the following compound. I'm going to do one of them, and then I want you to go ahead and do the rest of them here. So when we're talking about this, we want to think about building this from acetylene. So when we pick one of these, we want to actually start with drawing the final product. Okay, so in this case here, I want to start with, let's do, let's do this one. This one looks hard. So we'll do this one and see how to build it up. Okay, so we have to use all the reactions in this chapter, which means we have bromination of an alkene, we have hydroboronation of an alkene, but we have two of these. So let's think about this. So the first thing we need to do is back up and say, okay, let's draw our product here. So it's 1, 2, 3, 4, 5, 6, and we have a bromine here and a bromine here. Okay, so that looks like we could actually add HBr across both of the double bonds of an alkyne. If we were to do that, we would have a material that looks like 1, 2, 3, and 1, 2, 3. So now we have 6 carbons. So now 1, 2, 3, 4, 5, 6. So now we have 6 carbons right here. And so we need to make that 6 carbon material starting from acetylene. So the way we do that is we would have to back that up and say, okay, we got to chop this 2-member chain off and this 2-member chain off to get all the way back to acetylene. Okay, so this is how we're thinking about it. So we have to, what are we starting with? What do we have to react it with to get back? So now we know the first thing we need to do is put on this group here. So we're going to start with acetylene. And we're going to add sodium amide to deprotonate it. And then we're going to add some ethyl group with a halogen on it, like bromoethane. That's going to give us the butane right here. And then we're going to react that butane with sodium amide again and the same reagent, that ethyl bromide, sodium amide, that's a nitrogen there, and ethyl bromide, and that's going to give us our second addition there. So now we have no more alkynyl hydrogen, so we can't use sodium amide anymore. So what we're going to do is we're going to actually use 2 equivalents of HBr. Oh, we can't do that because that would put both of the hydrogens on the same side. Remember, whenever we add acids across a double bond, the hydrogen's always going to go to the more hydrogenated side. So if we added 2 equivalents of HBr, we'd actually have both of the bromines on the same carbon and 2 hydrogens on the same carbon. So we can't do that. So we have to follow a trick. Okay, well, we can add bromine across a double bond and it'll put 1 bromine on each of those carbons. So we have to trick it to do that. So we actually need an alkene. Wait, we just learned a reaction for an alkene that gives us that. So we know that we can take Lindlier's catalyst right here, Lindlier's catalyst, and that's going to give us our alkene. In fact, it's going to give us our cis alkene. Once we get our cis alkene, we then react that with bromine, and that gives us our 3,4-dibromohexane. Okay, so do you see how I used several reactions that we've already learned in this chapter to build this molecule? Okay, so I want you to practice at least a couple of those, and there's a couple of those on the homework as well. Questions on the synthesis of this part and why I had to use the Lindlier's catalyst on the alkyne to get to our desired product. Okay. So, and on one of these, you might have to use something like a boronation oxidation reaction or something to get that alcohol there. So, all right, questions on reactions of alkenes and alkynes. Okay, so let's do another one of these since we have nothing else. I'm going to do it over here. Let's do a reaction to form 2-butanol. Okay, from acetylene. Okay, so let's draw our product here. 2-butanol is going to be, let's see, our product we want is this 1, 2, 3, 4, and an OH right here. Okay, so that means we have to start with acetylene. Okay, so one way to start with acetylene is to go ahead and start with acetylene right here. And let's put on, so we have a total of 4 carbons. So let's put on 2 carbons. So we put on 2 carbons with sodium amide and a 2-carbon chain with a halogen on it, like bromide here. So that's going to give us 4 carbons. We have 4 carbons and we have a hydrogen at the end. Excuse me. So now we want to get an alcohol on there. Okay. So the best way to get an alcohol in there would be to do a hydron. Oh, hand raised.
How are you adding carbons if there's no carbons in a
Right, but that's what this does right here. Remember, we pull the proton off here, we get an anion, and the anion acts as a nucleophile and displaces the bromide on that other group. Okay, so that's that reaction of acetylide ion with a nucleophile and electrophile. The acetylide ion is going to displace some other group to create a new carbon-carbon bond.
And that will always be the product of NaH2?
NaH2 will only remove the hydrogen from the acetylene. And now you have to add something else to the reaction for that acetylene ion to react with something. So in this case, it's going to do this and produce a bromide ion, which is the much weaker base. Okay. So once we created that, now we have our triple bond from acetylene. Now we want to make sure we have an OH in that correct space. So I think we should reduce it down with Lindlier's catalyst to stop at the alkene. So if we lose Lindlier's catalyst, we're going to end up with an alkene. No, don't curve my line for me. with a total of 4 carbons in it. So we have butene now. Okay. And what's our reaction with alkenes to get a secondary alcohol? To get a secondary alcohol, you can add water across your double bond. You can also get a tertiary alcohol by adding a water across a double bond. However, you cannot get a primary alcohol with adding water across a double bond. You have to use boron. So in this case, all we have to do is use water and acid, usually H2SO4, and that will give us our 2-butanol. 1, 2, 3, 4. Okay. Anyway, go ahead and try a couple of these. What you're looking for is back up to figure out where you want to start and then put all the correct reagents to do each of those steps. And all of those reagents are found in this chapter. Okay? All right, so I want to talk a little bit more about the alkyl halide as a reacting species. Maybe that'll help. And so I'm going to jump to chapter 7. Chapter 6 is stereochemistry. I want to do that all by itself. So, but I think doing chapter 7 right here, these haloalkanes or alkyl halides, is going to tell us that what we need to know about that reaction. So when we have something like a halogen on an alkane chain, think of it as a leaving group. It's going to be displaced by something else, okay? So that you can think of it as a functional group because you can react lots of things with alkyl halides or haloalkanes and get lots of other products, okay? So let me explain a little bit about haloalkanes, and then I can come back and do another synthesis problem and see if we can't do that. Don't worry, I'm not going to make you do multi-step synthesis on an exam or anything. Okay, so the common structure is just, remember, any alkyl group is called an R, and any halogen can be called an X. So we typically call that the Rx is just means any alkyl halide we have, okay? Now, that's a nice sigma bond here, and both the halogen and the carbon are sp3 hybridized, okay? So we have nice symmetrical, electronic configurations, and we have a nice single sigma bond. So how do we name them? Well, because the halogen does not change the name because it is just a substituent, it's always going to be at the front of the material, and you're naming it for whatever the parent alkane is. So if you have 5 carbons in your alkane chain, it's going to be pentane, and then you have to locate where the bromine is. And just like other nomenclature rules, we're going to try to get the substituents on the lowest number first, and then we're going to alphabetize them. So if we do this last one here, we have a total of 5 carbons as our longest carbon chain. We have a total of 2 substituents. The methyl group is going to position that as the lowest number. So, and it's at the 2 position, and the bromine is going to be at the 3. So our final answer is going to be 3-bromo-2-methylpentane. If we have an alkene in there, we do the exact same thing. We name it for the alkene first. In this case, we have 6 alkenes in a, 6 carbons in a ring with a double bond. So that gives us cyclohexene, okay? And remember, whenever we're labeling alkenes, we have to go through both of the carbons first as 1 and 2, and then that puts us at our bromine at position 4. If we went around the other way, that bromine would be on position 5. So you must go through both of the carbon bonds, double bonds, to get to the lowest number. And then, of course, we can do our cis and trans here. In this case here, our OH is going back, and our chlorine's coming out. We have a cyclohexane. But the OH changes the name. So that's changing it to cyclohexanol. But the chlorine is still a substituent, and it's 1 carbon over from the naming one. So that gives us cyclohexanol. In this case, it's trans because the chlorine here is on top of the ring and the OH is on the bottom of the ring. Okay. So that's just how to name them. So, the halogens are always substituents. So that makes it really easy to remember. All right, so Unfortunately, because they are so common, there's actually some really common names for these materials that you might want to devote to memory for a little bit. One of them is this one right here, CH2Cl2. It's a very common solvent. It has a very low boiling point, and it's called either dichloromethane or methylene chloride. Okay, the dichloromethane is the IUPAC name. In this case, trichloromethane is called chloroform. Okay, so chloroform, used to be used for dry cleaning, and you've seen it in movies. They put that rag over somebody's face and they fall asleep immediately. It takes a long time. Don't do that. But it was originally used as an anesthetic, and many of the hydrocarbons are. Fluorocarbons are. And if we now extend it so that we have two carbons, we have to show where those chlorines are. Notice there's only one carbon in each of these, so there are no numbers. But in the case of this, we have two, and we have our closest substituent would be the chlorines on the first carbon. So it's going to be 1,1,1 dash trichloroethane. And this is called methylchloroform. Think about it. You have chloroform on this side and a methyl group on this side. So methylchloroform. The next one we have is another industrial solvent used a lot. It's called tetrachloroethylene. So imagine you have 4 chloros on an ethylene. The proper name is tetrachloroethene. That's the IUPAC name. But tetrachloroethylene is the ethylene plus the 4 chlorines. Right here. And that's another common name right there. So those, you'll see those more often than the IUPAC name for those. Okay. So I said they're also used in quite extensively. One of the major uses is as a freon, and a freon is used as something that can be turned from a gas to a liquid and absorb a lot of heat for refrigeration. So most of the freons started out as chlorofluorocarbons, so they only have chlorine and fluorine on them. The two most common are this trichlorofluoromethane. So there's 1 fluorine on here and 1 carbon, and so we get Freon 1,1. Okay, and on this one here, this is 2 chlorines, 2 fluorines, but 1 carbon, and we end up with Freon 1,2, or Freon 12. Okay, now because those are so bad in the ozone depletion, once they get into the atmosphere, they develop the hydrofluorocarbons. And in the hydrofluorocarbons, they got rid of some of the chlorine and replaced it with hydrogen. And they can be similar in effectiveness, but they have slightly different structures. So in this case here, we have a total of 2 carbons, we have 4 fluorines, and we have 2 hydrogens, and it ends up being HFC 134A. I don't know why it's numbered that way. But if we have 2 chlorines, 1 fluorine, and the 3 hydrogen, we end up with HCFC. So that's hydrochlorofluorocarbons. These are numbered differently, HCFC, in that right there. So these are very common, and a lot of them are being phased out for much more environmentally friendly parts. Question so far on the common names. I would worry about the methylene chloride and the chloroform and the tetrachloroethylene as the major things to think about remembering. Okay. So I said before, and when we talked about that acetylene ion, is that we had the acetylene ion come in as a nucleophile. It had a negative charge. It's a nucleophile. Okay. So it was coming in and it was going to displace the bromine because the carbon-bromine bond is the most stable. So that can definitely happen. The other thing that can happen is we can actually remove a hydrogen on the carbon next to the carbon with the bromine, and that would be the carbon with the bromine is called the alpha carbon, which means the hydrogen next to it is called the beta carbon. And so if we remove the hydrogen on the one next to it, we call that beta elimination. So our hydrocarbons have 2 things they can do. They can either be displaced and keep all sp3 hybridized bonds, all sigma bonds, or it can eliminate. And when it eliminates, it creates a double bond. So that's one way that we create our double bonds. Okay, so what one looks like that is if we just displace and keep all of our sigma bonds, we have done a nucleophilic substitution. So we had an anion come in with its electrons, creating that new bond, and kicking out the bromine with its electrons, giving us that bromide salt. If instead we remove hydrogen from one side and a bromine from the other with a strong base, we actually eliminate that and generate an alkene. So we can do both of those reactions with these halogenated materials. However, you must have a hydrogen on a beta carbon for it to eliminate. If you do not have a hydrogen, it will not do the elimination reaction. It will only do substitution reactions. Okay, so let's talk a little more about that substitution reaction. What's driving that substitution reaction? Well, the driving of the substitution reaction is you have a stronger nucleophile that is going to displace a weaker nucleophile. So what's going to happen is if you have a stronger Lewis base and you kick out a weaker Lewis base, the reaction is going to go in that direction. And because halogens are very strong acids, they're very weak bases and they're very easy to remove. So the other thing about nucleophilic substitution is we stay sp3 hybridized the whole time and we only have sigma bonds. So let's look at that a little bit. So we have our nucleophile, which is also our Lewis base, usually has a negative charge. It has at least a lone pair. It's going to come in and take those electrons and create a new sigma bond with our carbon. In the process, these two electrons of the old sigma bond are going to leave with the halogen and creating our new double bond, sigma bond, our new strong sigma bond, okay? And in theory, the bond created by that carbon and nucleophile is going to be a stronger bond than between that carbon and the halogen, also driving it to, driving the reaction forward. All right, questions about substitution reactions? Okay, let's do a little bit more and talk about the products we can get from substitution reactions. So I said nucleophiles tend to be things that have anions or they have lone pairs. So think nucleophile as Lewis base. So always look for a charge or a lone pair. In all of these different nucleophiles we use, we're actually going to make different products because of the nucleophile we choose. So in this case here, if we have hydroxide here, we're actually going to displace that halogen. Let's just say these are all methyl bromide, and so we're going to replace the bromide and create an alcohol, or in this case, methanol. If we take an alcohol and remove the hydrogen and use it as our nucleophile, we create an ether right here. So let's move away from oxygen and go to sulfur. We can create a thiol right here by using the anion on the sulfur, or if the sulfur already had a carbon on it, we're going to make a thioether or a sulfide. Now we can use another halogen as a nucleophile to displace to create another thing. That's a special reaction. We had a special driving force for that, and I'll talk about that later. In general, that doesn't only works if there's a special reason, because remember, this is a very weak base, so it's very hard to displace another halide, but it can be done under certain conditions. Now we have neutral nucleophiles or Lewis bases. That lone pair is the thing that reaches out and attacks it. And the first step in the reaction is to give you a protonated, notice all of these end up with positively charged species, but once we lose that proton to a base, it turns into, this would be turned into an amine. If we lose the proton from this, it would turn into an alcohol. And if we lose the proton from this, it would turn into an ether. So water is a strong enough nucleophile in some cases to displace a halide. But then you also have to have some kind of base nearby, and water is sometimes good enough base to transfer it to make it into an alcohol after that proton transfer. Okay, so halogens are easily displaced by nucleophiles, specifically the stronger the nucleophile, the more likely it is to displace it. The more acidic the conjugate acid of the nucleophile, the more likely it is to not work, because the most acidics are the HBr, HCl, HI, and those are weak nucleophiles. The other nucleophiles, the strong negative signs, oxygens or sulfurs, or even nitrogens, are much stronger. Okay, so do we see the variety of products we can make with this nucleophilic substitution reactions? Okay, so let's talk about how we decide which of these reactions is going to happen. Okay, so we have to talk about mechanisms. And in this case here, we're going to talk about a nucleophilic reaction. So we have a nucleophile. We're going to talk about that substitution reaction, but there's two possible ways it can happen. It can happen where both molecules come together and break and make a bond at the same time, or we can break the bond first and create a carbocation. So let's talk about the first one. The first, and it could be kind of some of both in there, but the two extreme cases are the one where two molecules have to meet somewhere to make our transition state happen and then go on to products, and both of the molecules have to be there. So we call that a bimolecular reaction, meaning both of the molecules, the nucleophile and the electrophile, have to be in the same place at the same time to make the reaction happen. Okay. So we call that Sn2, substitution nucleophilic bimolecular. Okay. So when we look at our energy diagram, our Sn2 is going to have one hump because of that formation of that one intermediate, where there's no intermediates, there's only the transition state. Which means if I have to have this molecule and that molecule there at the same time, the rate of the reaction depends on the concentration of both of the species. The haloalkane, which is the electrophile, and the nucleophile, right here. So that's another way to think about it, is if you have two things on your rate law, right here, it's going to be bimolecular, two things on your rate law. Okay. So, like I said before, both reactions are involved in the transition state, which means our nucleophile comes in, starts to form a bond with our carbon, and it starts to break the bond with the bromine, okay? And so we only have that single transition state, and at the end of that transition state, we have our new sigma bond, but we also have an inversion of the center, and we're going to talk about this inversion of center again in chapter 6. But notice it has to come in from this side and form the bond on the opposite side of where the halogen is leaving. Because you're forming a bond and breaking a bond at the same time, it has to come in that orientation. And when it does, notice how these hydrogens become trigonal planar during that transition state and then pop to the other side, like taking an umbrella and then popping it backwards. They pop to the other side when that new sigma bond is formed. Okay. So that nucleophile reacts on that center on the opposite side of the leaving group, leading to a new covalent bond, and whatever was attached to your carbon are now inverted in their configuration from where they started. Okay, so that's what that looks like. And we should have an energy diagram next, yes. All right. So in the energy diagram, we only have our nucleophile, our substrate or alkyl halide, and they are both in there, and the concentration of both is very important, because once we get enough energy to hit that transition state, it progresses forming that new sigma bond, and you go downhill and get products. And notice that in this case, the reaction is exothermic because it gave off heat during the reaction. Okay. So an Sn2 reaction has one hump in its energy diagram. Okay. So what's the other extreme? Well, the other extreme is if the first one is a bond is being made while a bond is breaking, then the other extreme means you have to break the bond first and then come in and make a new bond, right? So What that means is that you have to have the leaving group leave first. The bromine has to leave first, giving us a carbocation. And then once we have that, so now we have, it's only dependent on the concentration of the haloalkane. We only care about that one molecule breaking apart. Remember, that was one of those 5 things that can happen in a mechanism, is that we can break a bond to form a reactive intermediate. And that's what we do in the Sn1 reaction. It's unimolecular. It only depends on that alkyl halide breaking that bond first and becoming a reactive species. Okay, so what does that look like? Well, it'd be something easy like first step is you break a bond to form a stable ion. And in this case here, we have three groups on that carbon. So we're going to generate a tertiary carbocation, which is the most stable carbocation available to it. But this is also what we call the slow step or rate determining step. Breaking that bond, you have to have a reason to break that bond. And in this case, we're using probably solvent to help break that bond up a little bit to give us our cation and our anion right here. So now we have a reactive intermediate that can then go out, and now it is a strong electrophile because it has a positive charge. And that means even weak nucleophiles can react with it. Okay. So let's talk about that. So in this case here, the second step of the reaction would have any old lone pair can come and make that new sigma bond. And in this case here, we have OH groups or alcohols come in here, and it can come in from either side because our carbocation is at empty p orbital, and we have trigonal planar geometry. So if it comes into that one side, what we end up with is our protonated species here. So this happens first. We form a new sigma bond with that lone pair, but that hydrogen hasn't left yet. Okay, and this is a very fast step. Okay, now if it attacks from the other side, we see a slightly different structure, but it's the same thing. We have our new sigma bond with that lone pair, creating this other image of this thing. And then of course, the last thing to happen is to make it into a neutral molecule by giving away the proton and giving us our final product here. So this product here is now an ether because it's carbon, oxygen, carbon, and we have the solvent or methanol taking away the proton. So the whole thing had to happen because the bromine left first, giving us that carbocation. Now, with this carbocation, we have an opportunity for changing the attachment here. If it's attached this way, this side, that's going to give it one kind of isomer. If it's attached to this side, it'll give us another kind of isomer. We're going to talk about more than that in chapter 6.
So where did the bromine go in that reaction?
So the bromine is just kind of floating off into the solvent. It's being supported by the methanol.
So you wouldn't.
So
Okay.
once it leaves, it can go back, but it just goes with starting material. So
Okay. So when you write the final reaction, it will be the one you circled plus the bromine ion.
Yeah, there was bromine ion counterbalancing here. And because that's a strong acid, it's probably going to stay as this complex.
Okay. Thank you.
But you know, it's a low enough concentration. There's much more methanol than bromide ion because methanol is the solvent, and so the bromide ion is the back reaction is not going to happen very often. Okay, so what did the energy diagram looks like this? So we had to break a bond first, forming an intermediate, and then we had to have that intermediate react with lone pairs on a nucleophile somewhere. So we have 2 humps in our system. The first step is creating our carbocation, which is this intermediate, and the second step is making our new sigma bond right here. And in this case, we have activation energy is higher than the activation energy here, so this is a slow step. And it gives off heat, so it's exothermic. So we had our materials, we break our bond to form our carbocation, and then we form our new thing. So Sn1 reactions have 2 humps in their energy diagram. Okay, Sn2s have 1 hump, Sn1s have 2 humps in their energy diagram. Please don't get that confused. And you want to think about it that way. An SN1 typically forms a carbocation. So carbocations are always reactive intermediates. So I should see 2 humps in my energy diagram. Okay. So those are the 2 extremes. And so, some reactions can do a little blending of the others, and there's lots of things that affect which of these mechanisms will occur. So, but another problem with the SN1 reaction is if you form a carbocation, you might have it rearranged from the system. So that is something you always have to look for in your carbocation. If you can move a methyl group or a hydrogen to get a more stable tertiary carbocation, it's probably going to happen, and you'll probably have to show it in your reaction mixture, your reaction products. Okay. So what I said was, once we form that carbocation, it means that that nucleophile can come in from either side. And so what that means is we're going to end up with 2 different stereoisomers. Now, stereoisomers, of course, means in space, and isomers means that they're exactly the same except configured in space. We're going to talk a lot more about this in chapter 6, but I just want to show that when we have the formation of a carbocation, we always get 2 isomers out of it. One is where the species attacks from one side of the molecule, and one is where the species attacks the other side of the molecule. So if this attacks on the left side of the molecule, we get this isomer. And if this attacks on this side of the molecule, it gets this isomer. Is either side favored? No. Carbocations are trigonoplanar. It'll be a 50-50 mixture of being attacked on either side. There's no preference on sides. So another problem with SN1 reactions, besides rearrangement, is that you get this mixing of the stereoselectivity of your previous material. So even if you started with your R group, even if you start with pure version of it, this stereo configuration, you're going to get a mixture of stereo configurations in the end. Okay. So what evidence do we have that these nucleophilic substitution reacts? Okay. So what we do is a series of experiments that we know will affect one or the other. For example, does the structure of the nucleophile have an effect on the rate? In other words, is the nucleophile small? Is the nucleophile big? Because that changes which mechanism we're going to have. Does the structure of the haloalkane have a effect on the rate of the reaction? So a primary halogen is not going to form a primary carbocation. So I think it's going to not do some of those reactions. But a tertiary halide can form a tertiary carbocation, which is a more stable reactive intermediate. And so it might form. So that's why the structure of the alkane is important. And the structure of the nucleophile is important, because if it's too big to hit the reaction site, it might not be able to do that SN2 reaction. It might have to wait around for an SN1 reaction. What effect does the structure have on the leaving group of the reaction? If it's a really good leaving group, you can form that carbocation more easily. If it's a bad leaving group, then it might wait around until you have that SN2 type reaction. And then there's a role of solvent. Sometimes the solvent is the reactant, but sometimes the solvent can support that carbocation by bonding to it with hydrogen bonding or some nice electron pairs, or it can be disfavored because the solvent does not support that intermediate at all. So we will walk through each and every one of these as to how they affect our different reactions. Okay, so the first thing we want to talk about is nucleophilicity. Okay, nucleophilicity is basically a kinetic rate on how your nucleophile attacks under a certain set of conditions. So if it goes fast, it's going to be more nucleophilic than something that goes slow. Okay, so let's take an example where we look at taking ammonia. This is a neutral nucleophile. Those lone pairs are going to come, create a new sigma bond, and kick out that bromine at 25 degrees. Okay. So If we had the reaction where it formed the carbocation, it would form a primary carbocation right here. So that's probably not favored. But so that means we might want to start thinking about, ooh, what mechanism do we have that doesn't form a carbocation? And that would give us our SN2. Now, what other evidence do we have on that is, oh, okay. So this is the general trend on nucleophiles. Okay, and I want to describe a couple things about nucleophiles here. It's their ability to react. It's not necessarily their need to react, it's their increasing rate of reaction, okay, to form their bonds. So good nucleophiles are even these poor bases, these are very poor bases, but they are good nucleophiles. They're big, fluffy, they have lots of electrons on the outside, okay? Now, what are also good nucleophiles? These charged sulfur species. They're big, they're fluffy, and they have lots of electrons on the outside, and they're negatively charged. The next set are the oxygen anions, okay? Hydroxide, alkoxide, any methoxide. All of those are good nucleophiles because you have all that charge on that oxygen. Okay. Now, once we move away out of the good into the moderate, we're actually going to start to see some neutral nucleophiles as well. But only these two halogens are good nucleophiles, which puts the other two halogens as moderate nucleophiles. And then if we move that charge around off oxygen to spread it out onto two oxygens that we have on the acetate or the carboxylate ions, it's also a moderate. It's not a good nucleophile because that charge keeps passing back and forth between those two oxygens. And then we have, again, our neutral sulfurs and our neutral amines here. They all have lone pairs that can come out and be nucleophiles. Okay, so those are neutral sulfurs and neutral nitrogens. All right, now let's go to the poorest set. The poorest set is neutral oxygens, starting with water, and then the alcohols are just below it as far as poor nucleophiles. So when we think of poor nucleophiles, we're going to think of it's got to wait around for a carbocation. And then, of course, our carboxylic acids, if they're protonated, are poor nucleophiles. When we deprotonate them, they're moderate. But when we protonate them, they become poor nucleophiles, and they just have to use the lone pairs on the oxygen. Okay, so just kind of have a good idea of a couple good nucleophiles, a couple moderate nucleophiles, and look at that. Our solvents, our water and methanol and acetic acid are our poor nucleophiles. All right. Are we still there? All right. Okay. So let's talk about Sn1 reactions. Sn1 reactions, you have to form a carbocation. That means that a tertiary halogen is going to be more reactive than a secondary halogen. And the methyl and the primary halogens probably aren't going to react very much at all in that Sn1 reaction. So the relative rates are the tertiary is going to be faster than the secondary because of those electronic factors, because of the stability of the carbocation that it has to form in that unimolecular Sn1 reaction. Now, in an Sn2 reaction, because you have to have both molecules come into the same time, sterics are the biggest problem, okay? You have to be able to have that nucleophile come in and start to make that new bond. If it's too big and bulky so you can't make that good bond, it's going to slow that reaction down. So sterics govern your Sn2 reactions. Means your methyl is faster than your primary, which is faster than your secondary, which is much faster than your tertiary. Okay, so think about that. If you have to form a carbocation, it's ruled by carbocation stability. If you can't, if you can't do a carbocation, you're going to do an Sn2 reaction, and now it's all about sterics. How big a window do you have for those two molecules to come together? Okay, so let's talk about steric factors and why it's so important. So in this case right here, we've drawn an ethyl bromide. And in this case here, we have it as a space-filled model right here, but it's showing you that the two hydrogens are these two little lobes down here, and that methyl group is taking up this top lobe here. Okay. So if we look at that and we have a nucleophile trying to come in and attack it, the nucleophile can get really close to the carbon atom here in the middle and be able to, on the opposite side of where the bromine is, to be able to kick it out. So see, it's not very crowded. In fact, if those were all methyl groups, it would just be coming in 180 degrees from that. That's why it's so fast, okay? Because it can come in, start to form that bond 180 degrees away from its leaving group, in this case, broma, okay? But what if we had it the other way around? So where we had 3 methyl groups on our system here. So that gives us this electronic cloud, this electronic cloud, this electronic. Those methyls are 4 times or 5 times larger than the hydrogen, meaning that the only place we have to get that 180 degree attack is this little tiny wedge right here. Over here, we can attack from this entire we can attack anywhere from here to there, right here, and still get close enough to make that formation of that bond. So this is why sterics control this, and this is why methyls are faster than primaries, primaries are faster than secondaries, and tertiaries are very, very, very slow. Okay. Question on steric factors. All right, we got the last 12 minutes here. Let's keep our energy up. Okay, so that being said, if we compare electronic and steric factors, we can relatively easily decide which ones are going to do Sn1 reactions, i.e. for carbocations, and which ones are going to do Sn2 reactions based on sterics. Okay, so we have the idea that tertiary carbocations, tertiary alkyl halides, because of sterics, never do Sn2. There's very little chance of them doing Sn2 because of that whole backside of the molecule is completely covered. And it's a tertiary halide, which means it forms a tertiary carbocation. So whenever we have a tertiary carbocation, we're going to do an Sn1 reaction. We're going to form that carbocation. Okay, let's look at the other end here. When we have a methyl group there, we only have hydrogens on that back. It's easy to do that reaction as an Sn2 reaction. Every nucleophile can come in and react. And primaries are easy to react because it's very low sterics. In addition to that, the methyl carbocation and the primary carbocation are almost impossible to make in the lab. In a solvent, they almost always have to be made some other way. So that means they can never do Sn1 reactions. So they're always going to do Sn2 reactions. Okay, which brings us to our problem child of our secondary. Okay, secondary can do either, and it's all based on the size and or nucleophilicity and the solvent. So all those factors go into which mechanism the secondary alkyl halides are going to do. So these two sides are easy. Tertiaries are always Sn1, carbocation formers. Primaries and methyls are always Sn2, always going to do that bimolecular reaction. It's only the secondaries we have to worry about. So are there some general rules associated with that? Well, of course there are. And so this will help you define how to see which mechanism it's going to do. So the first thing is the leaving group a good leaving group? Can it leave easily to generate a very low basicity product? Okay, so when we think about that, start thinking about the conjugate base of our system and look for its acidity, and we'll see it follows the same order. Our HI is the strongest acid, and that makes it the weakest conjugate base, which makes it the best leaving group. Okay, so our best leaving groups are all these things that would have been strong acids. And then this is hydronium. This would have also been a strong acid. Okay, so all of those things that would have been strong acids if they had protons on them, makes them good leaving groups. They are the best leaving groups. The next is something like an acetate ion. The fact that we can delocalize that charge makes it a decent leaving group and makes it the most acidic of these other compounds if we add a proton. And then next comes water and alcohol and this amide right here. Hydroxide, methoxide, and the amide hardly ever act as leaving groups. Imagine losing hydroxide. Hydroxide would immediately react with everything around it. So that makes it a very poor leaving group. So the more likely you are to have a very strong acid if you protonated, the better the leaving group it is. Okay. So what else does? Okay. Now, we can get the OH to leave. However, we typically have to do it by protonating it first, because when we protonate it first, that makes water our leaving group. So even though hydroxide is a poor leaving group, and we cannot just displace it with a nucleophile, because there's no reaction that's going to happen because you have it hydroxide as a product. What you can do is protonate it by using the lone pair on the oxygen, getting to this oxonium cation. This oxonium cation can then take the electrons from the sigma bond and turn into a neutral species and a carbocation right here. Notice this carbocation here is going to be a tertiary carbocation. It would have been a tertiary carbocation here, but OH is such a bad leaving group, it doesn't leave at all. Because we have that leave as that neutral water, remember, it's that iodine, bromine, chlorine, water are the best leaving groups. We then get our carbocation, and now our weak, our moderate nucleophile chloride can come in and form our product. Okay, so just because you have an OH group on there doesn't mean you can't do it. It just means you have to use acid to make it a better leaving group. So acid makes the OH into a water leaving group, which is much, much better. Okay, so let's talk about the effect of solvent, okay? First of all, you have to define a couple things. We have two different types of solvents we are going to talk about. One is called a protic solvent. That's a solvent that can hydrogen bond, okay? Think of anything with an OH or that can hydrogen bond. This is a protic solvent. Okay. Now, because it's a protic solvent, it's got lots of ways to hydrogen bond, and it can be used to encourage the use of an Sn1 reaction because it can support that positive charge with all of those oxygens with lone pairs around them. It can easily support that carboxylic, that carbocation until the nucleophile comes in. Okay. The carbocation and the negatively charged leaving group can be well solvated. The negatively charged leaving group is solvated by the proton side of these solvents. The oxygens and the lone pairs stabilize the carbocation side of this. So that's why a protic solvent is a really good indicator that you're going to have an Sn1 reaction. You're going to form the carbocation. In contrast, an aprotic solvent is one that doesn't contain an OH group. So we think of common things like our ethers and our dichloromethane here is used as a solvent a lot. This is acetone right here. It's also has no hydrogen bonding. And this is a really, really strong and safe one called DMSO, dimethyl sulfoxide. None of these have OH groups with acidic hydrogens. And because of that, it cannot support the counter ions very well. These don't support ions very well because they only have dipole-dipole interactions. So it's very different. That's an ion-dipole interaction. It's a very weak interaction. So we're more likely to see that bimolecular reaction. So the one molecule has to come in, start forming the bond, and have the other group leave, because having the leaving group leave first is not supported by that solvent. So whenever we see a non-OH group system, start thinking about an Sn2 reaction. Excuse me. Okay, so we have leaving group ability controls our system. The solvent controls our system. Okay, what else controls our system? Okay. Well, those are the two things that really are our nature of our alkyl halide, and the solvent tells us a whole bunch about the different reactions. Okay, so our methyl group, because it can't form a carbocation, is always an SN2. So we don't have to worry about SN1 missing. Primaries, those have sterics, very low steric demand, and is almost always SN2. And so we don't have the SN1 reaction. We never form the carbocation. The secondary, we can do SN2 in non-protic or aprotic solvents with good nucleophiles. But if we have a protic solvent, we'll form the carbocation, and then we can actually have poor nucleophiles react because it already formed that carbocation. So what we're looking for in the secondary is, in this secondary system, I'm going to circle it separately here, is SN2 with a non-protic solvent and a good nucleophile, SN1 with protic solvents and poor nucleophiles. So that's why that one is right there in the middle. Tertiary here does not undergo SN2. It only does SN1 because of the stability of the tertiary carbocation. And the other thing about it is that because SN2 makes a bond and breaks a bond at the same time, we get inversion of that center when it happens. Because our carbocation here is trigonal planar, we get attack at either side and a mixture of products, if they can be different. All right, so that's the summary of the of SN1 versus SN2. I'm going to do one example because we have just a hint of time and show the examples that we can do here. So first thing we do is we look at our type of halogen here. Our halogen is on a carbon with two other carbons, so that's a secondary halogen. Oh no, it can do either mechanism. But wait, hold it. We gave us some tools on that. We are looking for protic solvents, and poor nucleophiles will make it go SN1. Good nucleophiles and aprotic solvents will make it go SN2. Here we have water, methanol as our solvent, and methanol is our reactant. Methanol is a poor nucleophile, so it must go SN2. I'm sorry, it must go SN1. It must form that carbocation. And luckily, it can only form a secondary carbocation, and so we're going to end up with one where the OME is sticking out, and one where the OME is joined back. Okay. See how I went through the process of saying it's a secondary. Let's figure out the product. Now, this is a primary. We're only going to do a substitution reaction. And means we're going to have iodine displacing bromide, and we only have one product. Okay, so take the last two and go ahead and run through those in your head before you get too far away, and see if you can identify whether we have a strong nucleophile, a weak nucleophile, whether we have a protic solvent or an aprotic solvent. Okay, and that brings us right to 12:20. So I'm going to go ahead and stop sharing, stop recording, and if you want to ask questions, please stay back.